Good afternoon. I'm very happy to open this first hybrid CFRG meeting in Vienna. So we do actually have quite a packed agenda, so I'll try to keep on top of it. So I'm Alexey Melnikov, my co-chairs Nick Sullivan and Stanislav Smyshlaev are remote this time. Let's get started. So as you probably know, the session is being recorded. We have minutes in CodeMD. I need a note taker. Can somebody please volunteer to be a note taker? Don't be shy. Don't stare at your laptops.
I'll help Chris, since I see he volunteered in the chat. This is Rich.
That would be perfect. Thank you. If somebody else can just sort of be a backup and help out with notes taking. Luckily, we don't need to do blue sheets in the former paper form. You logging into MeetEcho, whether it's MeetEcho regular or light, will automatically add you to the blue sheets. Rich, if you can mute yourself, actually. Your keyboard is very loud.
Yeah, sorry about that.
So IETF operates under Note well. You should be familiar with this already. If not, this is the slides with relevant RFCs. But one of the main points is always be professional, be nice to each other, be respectful, even if you disagree with a technical point. And we are governed by code of privacy and code of conduct. As a quick reminder, this is IETF research group, so we do research here, not standardization as such. And I will do a quick update on the document status. We have quite a few documents in flight. Well, actually, no. Any agenda bashing first?
Yeah, this is Chris Wood. I noticed the softer topic on the pseudocode and sort of specification discussion is first. I'd like to recommend, given the highly technical nature of the agenda, that be moved to the end, so we reserve time for those more important things. I'm happy to just, if we need to, in the interest of time, I can send an update to the mailing list to kick off discussion, but I don't want to take away time from the more technical topics that could use airtime.
Okay, that's fine. So you'll want to start with key blinding then?
Yeah, yep, right.
Okay, fine. That sounds good. Right. So my apologies for a small font. We're trying to fit in all the documents in with the life expired, but the gist of it is we have one RFC published, which is HPKE, RFC 9180. We have one document in RFC editor's queue in MISREF, which is aspect 2, which depends on hash2curve. And hash2curve is already an RSG review, so hopefully it shouldn't be long till it's approved as well. We have quite a few active documents. Pretty much everything was updated. VRF is waiting for the document shepherd. Kangaroo 12 is also waiting for chairs to review result of second research group last call. We get very few responses to this, so if you haven't reviewed the document or confirmed whether you still think it's a good idea, please send us a message or reply to the mailing list. Other noteworthy thing is actually the CFRG pairing friendly curves is, while it's expired, there is another co-editor for the document and it's being worked on. So hopefully it will be refreshed soon. Yes, Chris?
What's the status of the Ristretto draft? The last on the list, I do know it was updated to take into account the feedback from the crypto review panel review. So I'm wondering like what the next steps are. There are a number of documents that are building up dependencies on this, and it'd be good to move that forward. So I'm just curious what the next steps are.
Yeah, I suppose we should review it with my co-chairs, but it sounds like you're suggesting that it should move to research group last call soon. That will be
yeah, that's my understanding.
okay, sounds good. So the other thing is this is our regular slide about crypto review panel that serves three purposes. It helps CFRG itself, security area, independent stream to review crypto-related documents. We just we announced new round of membership in this last IETF with discussion about past performances as well as availability of different people. We basically kept everybody and added a couple of names, Virendra Kumar and Ludovic Perret. I think that's it. The other thing I actually just realized, and I forgot to have a slides on. In case you haven't noticed, we now have secretary. Thank you, Chris Wood, for being a secretary and helping organize us and help us with a website and GitHub in background. And now let's get started. Yes, Renee?
Good afternoon. I have a question on the crypto review panel. I noticed that sometimes a request is being made and then it takes an extremely long time to get the review done, even though people really promise to do it in about a month. And these are all people in the crypto panel who volunteered for this position. So it's not just a random person of the audience, right? So a particular case was last year of a document that I had reviewed already 3 times, and it took more than 4 months to essentially get any feedback.
So are you still waiting for review, or you just...
I'm not still waiting for review, but I think it's really hard.
Yeah,
it's really hard to accept a 4 months delay of people who promise to do something in 1 month, right?
Right, that's fair enough. Yeah, I think lesson here is chairs really should be on top of this and make sure that if reviewer cannot fulfill that, we should be able to find another reviewer.
Okay.
Chris? Okay. Christopher? Are you on crypto review panel or?
No, I just wanted to I had a follow-up question, but there's someone in the queue before me, and I don't want to jump the queue.
Okay.
I'm curious how many requests for reviews that sorry about that. I misattributed. I looked at the name in the queue. I'll fix that in the notes. I wonder how many requests for review the crypto review panel has at any given time. I'm just curious.
It really varies. Sometimes there are a couple of months or 3 months in a row, then there are none, and then sometimes you get 2 or 3 in 1 month, or even like twice as many. I would say about 2 or 3 requests per month on average. Right. Okay. Yes, Rene?
Sorry, just one more question. I looked at some of the, as we all know, the crypto mailing list is only sporadically being used for technical discussion. And I noticed that some documents apparently were ready to be to proceed based on one crypto review panel review, and there was absolutely a kind of a dead silence on the mailing list. And I always thought that crypto review panel was not a substitute for the normal operation of the CFRG. So I'm just wondering whether CFRG is kind of dead and the crypto review panel is doing something in the background, right?
No, it's absolutely not a substitute. That's they are basically working the same as the directorate. We should take offline any specific cases when you have concerns. Right, with this, Chris Wood, key blinding and signature schemes. I'm going to.
Can you accept the request? Oh, are you driving?
No, hold on. I can pass it to you.
That'd probably be easier.
Hold on. Let me cancel the request and then I should be able to just pass slide control. Okay.
Oh, awesome. I didn't know you could do that. All right. Yeah, thanks, everyone. This is a presentation of a new draft on this subject we call key blinding for signature schemes, joint work with Frank Dennis and Ed Eaton and myself. So for some context, consider this setting where you have what we call a single prover verifier, where the prover wants to convince the verifier of, basically a signature over a message, where the message is as input on the left-hand side to the prover, and the prover has a given key pair as input. The prover runs some signing algorithm, producing a signature, and sends the message, public key, and signature to the verifier. The verifier checks this particular signature and outputs basically a bit as to whether or not it's valid. In this particular setting, we basically want that this proof, the signature, is unforgeable, meaning that if you're given a tuple of message, public key, and signature, it's the verifier will only conclude that the signature is correct if it was produced by someone who actually has access to the corresponding secret key with overwhelming probability. This is just a basic digital signature scheme, but there are scenarios wherein you might not want the verifier to learn information about sort of the prover that produced the signature, or more specifically, you might not want the verifier to learn information about the signer's or the prover's long-term public key through either the public key used to verify the message or the signature itself. This particular property has a number of applications in practice right now. For example, Tor's hidden service identity blinding protocol uses this sort of construction for like signing things in such a way that you can't link them back to the original like service provider. It's also used in like cryptocurrencies for private airdrop. It's used in like Bitcoin hierarchical wallets to minimize state. And recently, we've found an application in Privacy Pass for a different type of issuance protocol that we call rate limiting. So it does seem to be a sort of common functionality, and the purpose of this draft is to try to basically, standardize it and specify it so that we can have interoperable implementations of it. And to sort of explain what I mean by this, I guess, not revealing anything about the prover, let's move on to sort of alternate setting where you have multiple provers now. So you have on the left-hand side 2 provers, prover 0, prover 1, each have their own unique key pair, and each are given the same input message to sign. You have some party in between prover and verifier, which I'm going to call the mediator, just for lack of a better technical term, and you have the verifier as before. In the setting, both provers are going to sign the message with their respective secret keys, send their triples over to the mediator, who's going to choose a random bit, and then decide to forward on the triple from either prover 0 or prover 1 based on that particular bit to the verifier. And the verifier will run the verification algorithm and try to guess the bit. So we asked 2 questions. Is this unforgeable in the traditional sense, like that I described earlier? If you're given, this triple of message, public key, signature, can you verify, or can you try to cheat the verifier? And the answer is yes, in particular because this is just a basic digital signature. But when you look at the unlinkability sort of property, that does not hold in this particular case. In particular because the verifier, you'll notice on the right-hand side, has as input the public keys of both prover 0 and prover 1. So it's pretty trivial to check whether or not prover 0 or prover 1 generated this particular signature by just looking at the public key or trying to verify the message signature under either one of the keys. So what we want is for this the verifier to not be able to determine the bit B with probability negligibly larger than half, no better than a random guess. And so this is where the sort of functional requirements come into play. We want an unforgeable signature scheme with these sort of additional properties, in particular that the per message public keys that are used to sort of verify a message at the verifier are independently distributed from the long-term prover keys. Moreover, that we want the signatures themselves that are produced to not leak any information about the long-term signing keys. And sort of jointly, this captures this intuitive notion of unlinkability that I was describing earlier. And our proposed solution is a signature scheme with key blinding. Functionally, what this does is it extends an existing digital signature scheme with 2 additional functionalities, one of which is a function for blinding and unblinding a public key. So given a public key and a blinding key, which in the syntax of the object is just another private key, you can produce a blinded representation of that public key, and then you can, of course, unblind it using the original unblinded public key. And we have this separate functionality, which is called blind key sign. We're open to name changes if it's helpful for clarity. But the gist is that if you run blind key sign with a long-term signing key and a blind key, the output signature will be valid under the correspondingly blinded public key using the same blind. So in this relation at the bottom, we have that trying to run the verification algorithm with the blinded public key over the message using a signature output from blind key sign succeeds or is equal to 1. And that's the sort of requirement or functionality, I guess. So if you were then to plug this particular scheme back into the multiple prover scenario before, you notice that the provers on the left are slightly different now. They have the same inputs as before. They have the same long-term signing key pairs and the same input message. But in actually producing a signature, they both generate a random blinding key, referred to as BK0, BK1 in this particular case, and they run blind key sign with that particular blinded key, producing a signature. And their triple that they send now to the mediator consists of the message, signature, and the blinding key. The mediator will choose a bit just as it would before, and it will use that bit to determine which of the blinded public keys to send to the verifier. So if the bit is 0, it blinds prover 0's public key with prover 0's blind, producing BK, and sends that over to the verifier, along with the signature produced by prover 0, and likewise for prover 1. So if you look at the two properties that we were targeting before, unforgeability has a sort of a signature scheme. It still has this property that the signature itself must have been produced by someone with the long-term private key with overwhelming probability. And by virtue of satisfying the sort of functional requirements, it also now has this unlinkability property that we want. In particular, the blinding key, or the blinded public key, BK, is independent from both of the long-term public keys, PK0 and PK1, the provers. And like similarly, the signature itself is independent from the long-term signing keys. So the triple itself reveals nothing about either prover 0 or prover 1. So it intuitively, the verifier cannot guess the bit with, it cannot do better than a random guess at bit B, which is the property that we want. That's effectively it for the functionality. It's very simple. The EDDSA variant is in the draft, building off of RC 8032. It only covers the pure EDDSA, none of the context or pre-hashing variants or whatever. That's very straightforward. It's often used as an offhand demonstration of the concept in academic literature and whatnot. There also is an ECDSA variant in there as well. This is a bit different in the sense that it's not doing the obvious thing, I guess, that you would do for key blinding. I can elaborate if people would like, but it's different enough that we're doing security analysis to determine whether or not it is indeed safe. But the intuition is that it is correct. There are also a couple of implementations, thanks to Frank and myself, and other people are working on them as well. It's fairly simple, straightforward draft to implement, and there are test vectors available for those who'd like to implement it. And as I said, the security analysis is underway. We hope to make those results public as soon as they are done, to gain confidence in the constructions. But as I said, the EDDSA one is fairly straightforward and intuitive. It's the ECDSA one that is the more interesting variant. And with that, I guess I have two questions for the group. The first of which, do folks find this to be a compelling use case and problem worth working on and trying to solve with this construction, signature schemes with key blinding? And secondly, are folks interested in adopting this as an initial draft to do exactly that? And I will pause here for questions, and I'll read the chat.
We have 3 minutes for quick questions, if there are any. I think the question of adoption we'll probably discuss between chairs and might take it to the mailing list.
Works for me. If folks are interested in more clarity on anything, the draft link, the draft has a link to the repository where it's being developed, and of course we welcome any and all of your feedback and contributions.
Christopher, are you on this topic?
My question, I would like to understand a little bit more about what changes you made to ECDSA or had to make.
Right. So the ECDSA variant, the intuitive thing that you might do is given a private ECDSA key and a blinding key, which is also a private key, you might just multiply the two together. And similarly, you might multiply the public key by the corresponding blinding key, and ergo have a blinded representation of both the private key as well as the public key. Unfortunately, there's this there's a body of work on related key attacks and how they can be used to produce forgeries for Schnorr-like signatures as well as ECDSA. And in particular, this sort of naive way of blinding an ECDSA public and private key does lend itself to forgeries. I can point people to the relevant references if they're interested. So the tweak we made was to basically, rather than maintain sort of the algebraic relationship between the blinding key and its impact on the I'm using the word blind a lot, but okay. The trick was to rather than maintain the algebraic relationship between the input blinding key and the output blinded public key, to hash the input blinding key to a scalar to sort of blow away this algebraic relationship and make it so that basically you need to produce a collision in this hash in order to produce a forgery. So the construction does kind of depend on security in the random oracle model intuitively, but that's effectively the gist. I wish I had it written down in slides, but perhaps that vocal description was not overly clear. But Chris, I can send you pointers to the diff where it was included, if that would be helpful.
Okay, so unfortunately the queue is closed and we are a bit out of time on this topic. So let's on the mailing list.
Okay, thanks, Maxi.
Right, thank you. Stephen, you're next. Do you want me to drive slides? Yeah. Fine, I'll do that.
Somebody was very tall.
Just hold on 1 second.
Okay, next slide.
Hold on. Just 1 second. Okay. Okay.
Great. So I see there was like 100 people in the session. So I hope to get some feedback on this, even if it's just kind of a sense of what people think. So the Lake Working Group is defining a protocol called EDHOC for authentication and key establishment for small devices. It's, you can think of it kind of a bit like TLS, does the same kind of thing, but it's really tailored towards kind of small packet size, few octets to be emitted. And if you care about the requirements, you can see them there. So again, like TLS, there's kind of a concept of cipher suites, and in those kind of cipher suites, there's a signature algorithm represented for authenticating one of the parties. There are suites defined that involve ECDSA and EDDSA, and that Lake Working Group is trying to figure out how to do, which signature algorithms should be part of a mandatory to implement set of cipher suites. And as always, there's lots of argument in IETF working groups about that, but that's not what we want to talk about here. So next slide. So in this particular context, There's kind of an additional argument to the usual MTI cipher switch selection issues. Essentially, where an adversary controls a provision device and can mount, fault injection attacks and extract a signing key. And for the kind of applications the ad hoc protocol is designed for, that seems much more likely than for a TLS as used in data centers or whatever. And thanks to Rene for bringing this up. And there's a link there to the thread from the Lake Working Group. And the context is small, relatively inexpensive commercial devices that are provisioned. Private key is probably not that well protected. So if you open the device, it won't be zeroed. But hopefully, you can't just connect to a UART and read the private key from the file system. And private key extraction could be significant because then perhaps you could pretend to be a controller to some actuator and cause damage. So next slide. So I know almost nothing about fault injection, but I did find a few papers that were interesting. So the first one I thought was actually pretty good for me because it actually explains how you can do fault injection via kind of a low voltage attack. It's a little bit old, but it's a really nice explanation of how these attacks can be kind of mounted in a realistic environment. And it includes an example of, it's not a novel attack on RSA signing, but it's in that paper there. It shows how such a fault injection attack on reading from memory can leak an RSA private key. There's also another one about ECDSA from the similar time frame. Same kind of attack where you've got a fault injection on kind of memory reads. Although the second one is a simulation as opposed to an actual demonstration. But that's on ECDSA. And then there's another one on EDDSA, which is, in that case, it's a power analysis attack rather than fault injection. So those are kind of useful papers. And I think what they seem to show is that at some level, all of the possible sensible options we have to choose from might be vulnerable to these kind of attacks in this kind of context for these kind of devices. Next slide. So one of the points being raised, that was raised in some of the discussion here, is that EDDSA is deterministic. That might help the attacker as opposed to the randomness in ECDSA. But of course, you can have a bad random number generator, as has been seen. And there have been some suggestions. John Matson has a suggestion for adding some noise or some more randomness into EDDSA. And again, I don't have a personal opinion on these, just to note that these issues have come up. So next slide. So the ask is, I think it boils down to two questions. I mean, we seem to have three kinds of signature algorithms. We may, assuming a working group wants to pick a mandatory to implement Cipher suite with a signature algorithm, is there really much difference here between them in this specific kind of attack context? So, we could do with some help if that's the case, or assertions that from knowledgeable people that it's more or less the same, or it's different for different ones. Or could CFRG develop something that's usefully better in this attack context? So for context, the Lake Working Group has kind of currently, picking their MTI choices has kind of oscillated over the last number of months. I think currently they've landed on just saying just 3256. They probably won't want to wait for an answer, so it's not a question where we need the answer right now and are kind of waiting on it and insisting CFRG do stuff. But I think it's a generic problem particularly for this class of device. And again, there was a thread on the CFRG list that didn't really reach anything I thought was a clear kind of answer. Hence this presentation. So last slide. So again, just to summarize, the attacker here controls a provision device, is able to mount a fault injection attack, let's say, and extract a signing key. I described the kind of device, and the two questions there are, which of those are, if any of them are kind of good to recommend as a mandatory to implement Cipher suite, and in that context, and is there anything better that you could recommend? And I hope to get some input. Does anybody know about this topic?
Rene?
Rene.
Quick remark. So indeed, I raised this topic at the Lake Working Group. I think the main issue is really the determinism in the noise generation. So as as long as one can fix that with EDDSA may be fine. If one cannot fix it, ECDSA already doesn't have this determinism as long as one ditches RFC 6979. So I think it can be easily solved, but it has to be addressed if one wishes to use EDDSA, and otherwise ECDSA with P256 would be a viable option, in my opinion.
So that the audio chopped a bit there, but I think you were basically saying ECDSA is better, which then leaves me wondering about those other two papers that I referenced as to.
Actually, Steve, I didn't say ECDSA is better. ECDSA is only better because the nonce generation is non-deterministic. If EDDSA would be specified in a non-deterministic way, then the problem goes away, as I identified.
So again,
hope that makes it clear.
So that leaves me wondering about the paper that I referenced that has a fault injection attack on ECDSA.
Well, the whole side channel attack arena is quite large. I have more than 1,000 papers on this topic. So obviously there are attacks on all different variants, but there are attacks that can easily be prevented that take advantage of deterministic behavior.
Sure. Yeah.
You still need to know what you're doing. You cannot just claim that, right?
Right. But again, just from the point of view of trying to pick something, if there are lots of if we're talking about a mandatory to implement Cipher suite, we're asking everybody to implement it, and if there are known attacks against all relevant signature schemes, they happen to be different attacks, but they're known in this context, then it's not clear to me that one is better than the other.
I think the problem is that lots of attacks are also with respect to, for example, OpenSSL versions that are known to be broken, and you still need to be slightly competent in terms of implementing signature schemes.
Okay, John?
Thank you. Thanks, Stephen, for raising this discussion. I think it's very helpful. Regarding two, I think Ilari summarized nicely on the list why we need 3 different alternatives, purely random, purely deterministic, and a mixture of the two. They all make sense in different settings. I think we can do better. And I think what maybe more a question to the chairs that should be discussed either here or on the list later, but how do we progress with draft Matson? There was quite large support for adopting. Then during the adoption call, there was a discussion about a potential alleged IPR on it. Do we have should we have a second call for adoption now when that is known? Stephen also said on the mail that he could declare an IPR statement on the draft. That would of course be used in court, as Stephen Farrell has analyzed this IPR, and he definitely thinks it applies. So there's negative things with that also, but it would raise to any implementers and users that somebody has claimed an IPR.
Yeah, sorry, I'm actually the responsible chair who dropped the ball on this. I think, yes, we need to rerun the adoption call with IPR disclosure.
And just to clarify, if I made a third-party IPR disclosure, it just says you're on notice that something exists. It doesn't say I claim it is relevant.
I think the lawyer in court would say that anyway. I agree with you in principle. Yeah, that sounds great for the second adoption call.
Okay, yeah, let's record this as an action item. Philip?
Yeah, I was just going to point out that since we're going to be doing we've got the threshold signature work. We're going to have things that look like non-deterministic signatures as far as the verifier is concerned anyway. In that I have never considered the idea of relying on a signature value to be a non-deterministic function of the input in a protocol to be a sound move. So I think that we should definitely allow for some form of signature with a deterministic component. I think it still makes sense to require people to blind the input, blind the random number in some deterministic way, and then apply the non-deterministic input so we get as much robustness as possible. But I think that we need that anyway. What I'm a little bit nonplussed about it, I've never understood why people want to put signatures into key exchange protocols. If you're doing a key exchange protocol, Diffie-Hellman does a key exchange, and you can build robust systems on top of Diffie-Hellman, as the Signal folk have proved, and they've got a proof of correctness of that. I would just steer clear of anything to do with signature, because if you sign something, you create a non-repudiable proof that somebody was involved in that communication. And that's dropping a piece of information that I simply don't want to drop unless there is a good reason to drop it. Oh, just a thought.
All right, thank you, Philip. Bart?
Bart, you need to hit the unmute button as well, I guess, or request audio permission. Yeah.
Okay, does it work? Okay.
Yeah.
I heard Steve asking some questions, and maybe I can help by simple clarification to this. So, in a differential power analysis attack, you need some secret information and some variable data. And by actually making this, if you can avoid that by having a signature, you can avoid a DPA attack. But there is other attacks like simple power analysis or fault attacks that are kind of orthogonal to this, and that are not helped or helped by having variable data. And so this may answer your question that I don't think there is any signature scheme that is by itself robust against any of these attacks. You always have to look at your implementation, but particularly having deterministic involvement or generation of the nulls in a way that is not randomized, you will make DPA attacks harder. I hope that helps.
Thanks, Bart. Yeah, that does help.
All right, thank you. Tom
Wiggers. These kinds of attacks, fault attacks, they aren't just limited to crypto, right? They allow you to sort of, in my understanding anyway, skip arbitrary instructions that your target is doing. So in the case of signature verification, they might also just skip over the entire verify call altogether. They could also skip over a random number generator. So this is, I think, a type of question that you should consider wider than just what kind of crypto do we use and how vulnerable is that, but also how do we structure our implementation in the first place? Because if the crypto is not getting called, it will not really have mattered in the end.
Sure, I think that's entirely true. It's a little bit of, so I think the concern here is an adversary gets control of a device and manages to extract a private key.
Yeah.
And then can do what he likes with it. So, so it's a little bit different from that, I think. But I absolutely agree with what you say.
All right. My apologies. I'm not going to pronounce it correctly. Guilin?
So actually, I just have a simple question. So what does it mean you call it MTI signature? What is MTI?
Oh, sure. Apologies for not explaining it. So when IETF working groups are developing protocols, typically they would like to specify a mandatory to implement. That's what MTI stands for. Set of options so that we increase interoperability, because we hope all implementations will include them. So the question here really is which of these signature schemes would we like everybody to implement?
Okay, got it. Yeah, thank you very much.
All right, thank you. We have one action item, and you got some useful feedback, I think.
Sure. So I guess the action item is on John's draft, I guess. I think I suspect the same question might arise with CTLS for if it was deployed in similar environments that Lake is envisaging.
Mm-hmm.
So if the answer is, as Bart says, that there's different attacks, but so there's no real difference because you can mount one attack or the other, then it would be great to kind of have a sense of that so that we could feed that into IETF working groups.
Okay. I suggest interested party are welcome to continue on CFRG mailing list.
I can certainly try again.
Okay. Well, I think now that you kind of raised awareness of this, maybe there might be more uptake for this.
Yeah, hopefully your presentation may have helped. So I'll start a thread, and if you deal with John's draft, I guess that's the two actions, I suppose.
Okay.
Great. Thank you.
Sounds good. Next is Chris Patton. Hold on, just yeah, let me. Okay.
Only my second CFRG talk, so I don't remember how to run the slides.
So you should have now control for driving slides.
Okay, let me test it out. Hi, everybody. It's fun to be on the big screen once again. Okay. All right, so I wanted to give a quick update on an individual draft that I've been working on with Richard Barnes and Philip Schopman. This is called Verifiable Distributed Aggregation Functions. And I'm going to give a quick overview of this, so if you missed IETF112, don't worry about it. You should get all the context that you need. Speaking of context, so what this is really about, we've recently formed a new IETF working group called PPM, which stands for Privacy Preserving Measurement. That group is meeting tomorrow, by the way, for anyone who's interested, please attend. And the goal of this working group is to standardize cryptographic techniques for what we call privacy preserving measurement. And we're thinking, right now we're mostly thinking in terms of like multi-party computation. So what PPM kind of means is you have a bunch of users and you're interested in aggregate statistics about these users, but you don't want to see their individual measurements in the clear. And so you want to run some sort of multi-party computation to make sure that you don't. So right now we're working on what we're calling our first protocol, and we're hoping that it'll be adopted by the group as the first document. And what this does is specify the end-to-end verification and aggregation of measurements over HTTPS. And this document, the VDAF document, is kind of the core cryptographic component of the PPM protocol. So my objective for this talk is to explain to you what this draft is about. And I also want to ask the CFRG if this is ready for adoption by the working group. Okay, a quick overview of VDAF. So the main cryptographic technique we're going to use is just simple secret sharing. So the way our architecture works is you have a bunch of clients, and they're going to be sending their secret shares of their measurements to two different aggregation servers, or two or more aggregation servers, I should say. And then aggregates are collected by another party called the collector, and who assembles the final result. So in this first step, the sharding step, each client is going to split its measurement into input shares, as we call them, and sends one input share to each aggregator. And then in the next step, for each set of input shares, where the aggregators are going to engage in a multi-party computation to basically, which has basically two goals. One is to verify that the input shares that they're getting correspond to a valid measurement, and the other is to basically prepare the input for aggregation. And I'll explain. I'll get into that in a little bit. And then the last step, so the preparation step is kind of the core meat of the protocol, and then all they have to do after they've done this step is combine their output shares into aggregate shares locally, and then send aggregate shares to the collector, and the collector combines these aggregate shares to get the final result. So I'm going to give a couple example protocols, so hopefully this will be clear in a moment. The spec currently has the goal of the spec right now is to actually specify 2 instantiations of a VDAF. And the first one is Prio, which many people might be familiar with. It's kind of been in the ether for a while now. And in this protocol, it's very simple. A client is going to encode its measurement as a vector over some finite field, and it's going to split that vector into secret shares and send one vector to each of the aggregators. And then to prepare these input shares for aggregation, they're going to just make sure that the vectors that they have sum up to a valid input without actually learning what the input is. And then all they have to do in the aggregation step is sum up their vectors, and then all the collector has to do is sum up the aggregate shares. Now there's the other protocol that we want to specify is called Poplar. So this is another paper from the same group of folks. Now the problem that this solves is the heavy hitters problem, and this is where you have each of the clients' measurement is an n-bit string, and you want to know which of these strings occur at least some number of times, so t times. So in our example here, we have 3-bit strings, and only 2 of those strings occur in that set more than at least 2 times. And the solution for this problem, I won't go too much into the detail, is called an incremental distributed point function. And what this allows you to do is kind of query so clients are going to compute what are called IDPF shares from their input, and what this IDPF share allows you to do is to kind of query your the input on a candidate prefix. So you can ask so if your input, for example, is 0, 1, 1, you can ask, is 0 a prefix of the string, which it is, or is 1 a prefix of the string, which is not, etc. And so what what the query, the result of the query on your IDPF share is a share of this answer, like yes, this is a prefix, no, this is not a prefix. And what you can do with that is aggregate them into shares of hit counts. So basically, your aggregate share is a secret share of the number of times a candidate prefix occurred in the set. So this turns out to kind of nicely fit this shape with a few minor tweaks. So in the sharding step, the client generates its IDPF shares from its input string, And now in the preparation phase, we're going to do something a little bit more complicated. We're going to evaluate our IDPF shares on a set of candidate prefixes, but then we need to verify that the output is well formed. Basically, we should only have each aggregator should only have a share of a vector where where you can only have one candidate prefix for like a given input. So yeah, so yeah, I think I'm running a little bit low on time, so I won't get too much into the weeds here. Okay, so there's this IDPF share evaluation, and then verification that the output share that you get is well formed. And then in the aggregation phase, all you have to do is sum your output shares into a share of the hit counts, and then you hand those to the collector. And so the way this is going to help you find the heavy hitters is you're going to run this, the collector is going to run this protocol, basically prepare, aggregate, unshard several times with several different sets of candidate prefixes until it finds the set of heavy hitters. Okay, so very quickly, we've made a lot of progress since IETF112. What we have today is basically a complete specification of PRIO and including a reference implementation that generates test vectors. And there's at least one implementation of this that's pretty fast. So the next things I think to do is the next chunk of work is to complete the spec for Poplar. There are a couple of implementations of pieces of this. It's a little bit more complicated. None of them interoperate yet, so this is why we want to have a spec in the CFRG, especially because people want to implement this. The other things we need, we're working on security analysis, and we'll need to flesh out the security considerations. And of course, the hope is that this, drives cryptography researchers towards directs cryptography research towards the design of VDEFs that solve different private data aggregation problems. Yep, and so there's a few other open issues, but I think in my view, this is based on what I've seen. I'm kind of new to this. I think this document is mature enough to start working on it in the working group. I'm curious to know if people are interested and what would be the next step.
Comments, questions? Chris, go ahead.
Yeah, thanks, Chris, for the presentation. I'm obviously supportive of this, the group adopting this as a research group item. Well, within the purview of CFRG to work on bringing something like this to the rest of the industry by standardizing it. And as Chris said, we have a number of implementations already. PRIO especially has a lot of experience in running code, so this seems like kind of an obvious candidate for adoption, and I would like to see that happen. Thank you.
Stephen?
Hey, Stephen, yeah, I'd similarly like to see something that can support PPM adopted and produced by CFRG. I think it's the right place to kind of work on these functions.
Okay. Chess will talk to you, Christopher, and I think tentatively we're happy to do adoption call, but we'll just double check between ourselves.
Thank you.
All right. Okay, Asgcm Exploit. Next. Okay.
Can you hear me? Okay.
Yes. Shall I share? I'll share and pass to you controls again.
Great, thank you.
Right. It's a new and exciting feature. Oh, hold on. What's happening? Oh, Christopher, you need to stop sharing. Okay, right. Thank you.
Okay. Oh, great. I have the slide controls. Great. So, yes, thank you. This is about a rather applied topic. It's about an exploit of Asgcm authentication tag for hidden communications. It's a work that has been co-authored with Alexander Hartl, who's on site, and some other colleagues from academia and some from industry. So next slide. Yeah. First, about hidden communication, just very briefly. So malware, it's about malware communication, hidden malware communication in critical infrastructures. Initially, so malware needs network communication to unleash its destructive power. And initially, malware used explicit communications, meaning communications that use dedicated messages on TCP, UDP, etc. And nowadays, malware becomes increasingly stealthy, meaning it tries to hide within existing legitimate benign communications. In the example below, you have Alice at the left, Bob at the right. They just exchanged some benign IP datagrams, and Mallory somehow got access to an ASN on the path and is communicating with Eve just by exploiting some of the unused fields or less used fields like TTL, etc., that are not that apparent, and so they misuse existing communications. Can happen rather as a covert channel, so IPPTL, flags, options, inter-arrival times, modulations, or you could use also some nonsense, random numbers, etc. Now, if we have this critical infrastructure and we want to harden this infrastructure, we need to assume that any system is vulnerable. That is, the question is not who discovers the question is not when or if a 0-day is discovered, but who discovers this vulnerability and when. What is typically done in industry is now to protect the key material using so-called CKMDs, crypto key management devices, so trusted platform modules or smart cards that are uncompromisable, and so they protect the key material physically and offer some well-known APIs. So in the case of compromise, shown as red, so even if a IoT device, for instance, a smart meter is compromised, this key material cannot be leaked because it is physically shielded, meaning there are just some well-known APIs to encrypt or decrypt using these keys. And this can be either a hardware module or it can be networked, as you see at the right. And the question that we ask ourselves is, can malware exploit cryptography for hidden communication in these hardened systems? And the answer is obviously yes. AES-GCM, I'm not going into details. I just want to outline. So we have some input parameters to the algorithms. We have an initialization vector. We have some plain text message blocks. The key material that is protected, so we don't believe we can change this or we can find any exploit related to it. And we have output parameters shown in red, so ciphertext blocks and the authentication tag. Now, concerning the initialization vector, there have been already some discussions on the lists during the definition of Asgcm and deployment. It was a discussion whether initialization vectors should be chosen randomly, and the answer was no. So a clear recommendation not to do so, because in particular of this ability for hidden communication. So it is recommended to use deterministic counting initialization vectors. When using such a CKMD, the state keeping is difficult. These CKMDs are typically stateless devices, meaning they just map a specific ID and a specific message to a specific key. So deterministic initialization vectors should be likely managed by this requesting device. If we now consider a legitimate device communication in this context that we have analyzed, we have at the left a sender application that uses a kind of security proxy. That is a sender application, a benign one, just wants to send some plain text P to a receiver application at the right. And on this behalf, it uses a security proxy consisting of a sender and a sender CKMD. So if the sender is compromised, nevertheless, the sender CKMD protects the key material. What it does, so if the legitimate message arrives at the sender, it computes a new initialization vector, sends an encrypt request with a plain message initialization vector to the CKMD, which encrypts the message and gives back a ciphertext and a authentication tag, which is then transmitted to the receiver security proxy that decrypts all of this information, so passes cipher, initialization vector, and authentication tag to the receiver CKMD. However, please note that this receiver CKMD typically will refuse the decryption if one of these three parameters is faulty, meaning if we have a faulty authentication tag, it will not decrypt. And as a response, we get a P, the plain text again, and the receiver proxy then forwards this message to the receiver application. What can we now do? Or two observations firstly. So GCM works similar to stream ciphers. That is, we can decrypt by encrypting with the same initialization vector, and we can decrypt by circumventing the authenticity verification. That's a problem common to other counter encryption modes. Mapping this generic sequence diagram to an IoT infrastructure, think of a smart metering infrastructure, for instance. You have IoT devices that are potentially compromisable. So you have physical access to these devices. They protect the keying material, but nevertheless, firmware exploits, 0 days, etc., can lead to these devices to become compromised. And we have not just one device, but we have tens of thousands of such devices that work together. These devices are concentrated, so the traffic from these devices is concentrated and forwarded to an edge server that is reachable from the internet and therefore might also be compromisable. An IDS just supervises the communication to this edge server, and it is worth noting that passing any keys to this IDS is not advisable. We know about SolarWinds, Sunburst, Orion exploit. So giving keys to and administrative power to IDSs is not that good design decision. Finally, this edge server then uses a network CKMD server to pass the encrypted data to it, and then forwards the information to an application server. What we want to do is to implement some subliminal communication between a smart meter and an edge server without this information exchange being visible to the outside. So we want to exploit, and in particular the authentication tag has shown to be available for this, and want to circumvent the CKMD authenticity verification in the receiver. But please note that this communication is bidirectional, so we can use exactly the same approach in both directions. And the solution is quite straightforward. So Subliminal sender is compromised, subliminal receiver, so these security proxies have been compromised. They cannot leak the key material, but nevertheless they can act. Whenever a sender application or sends a legitimate benign message that is to be encrypted, the subliminal sender chooses an initialization vector, encrypts this information, and what it does is simply replace part of the authentication tag with the subliminal message to be sent to the receiver, and sends this message together with the modified, so the subliminal authentication tag, to the subliminal receiver. The subliminal receiver uses this stream cipher property. It simply takes a random string of length corresponding to the ciphertext, encrypts these data using the initialization vector, and gets a CR, so a ciphertext of the random text, and a tag that it doesn't use. Now, unfortunately, by XORing the random text and the ciphertext, we obtain the cipher. And by XORing the cipher with the ciphertext, we get the plain text. So subliminal receiver now, using this encrypt operation, has access to the plain text. It has, from the authentication tag, it obtains the subliminal message, can take an action, a destructive action, and forwards the message, the plain text, to the receiver application. So from an outer world perspective, that's absolutely legitimate. The only issue is that this subliminal information here needs to be somehow hidden by the subliminal sender. Can we do better? Yes, of course. We can change the entire process just by doing exactly the same process, and this hidden information is XORed into the authentication tag. That is, instead of replacing, we XOR it with the authentication tag and get encryption of our hidden information for free. Process at the receiver is absolutely the same one. We get the plain text, but wait, we do not have the authentication tag. We need the authentication tag to extract the subliminal information. What do? We encrypt once more. So we encrypt the plain text with the initialization vector, get back the authentication tag, and then by decoding so by XORing the authentication tag and the subliminal tag, we get the subliminal message. That's it. So from an outer perspective, without having the key material, it's almost impossible to identify that something has happened here. This exploit is agnostic to protocol semantics, can be used in any context, and cannot be destroyed by intermediate nodes, because otherwise the legitimate authentication tag is destroyed. Without leaking the secret key to some observers, it's impossible to identify that the authentication tag is faulty, and the capacity is usually high because message authentication codes are typically transmitted frequently, so such reports or messages. Moreover, the location of the sender of this hidden information can be anywhere on the path where it can access the authentication tag, so it needs not necessarily be collocated with the device. I'm getting short of time, so yes, mitigations. Thank you. You have already standardized GCM SIV, so synthetic initialization vector, which solves exactly the problem. So it is the issue is that we have initialization vectors that can be repeatedly used. It's clear that this should not happen, but it happens in this setup. We can generate IVs on the CKMD, but this can lead to CKMD-originated subliminal channels. And we have a deployed mass of systems that need to be maintained. That is, we could use distinct keys for each direction, forward, reverse, or we could use the initialization vector. Segment a set of initialization vectors for each direction. And I'm almost done. So just combining the CKMDs with the GCM encryption can show security shortcomings. And yes, obviously, GCM SIV is recommended or some remedies, but it's a general architectural problem, and yes, one should consider this opportunity. You have a link over here that leads to the paper. If you don't have access, please drop me a note and I'm happy to send you a pre-published version. On the last slide, you have some information on the project that we're doing, and this was a result of this project. So yeah, happy to take questions, and thank you for the opportunity to present.
Okay, we are slightly behind on...
yeah, I'm sorry.
No, it's all right. I logged the queue, so 2 questions. Jonathan first.
Jonathan Hoylands, Cloudflare. One way you could potentially detect this is in use is surely by having some middleman munge the authentication tag, right? They just mess it up. And the receiver should then reject the message, but it won't.
Yes, sure. There are many. So for instance, you could also intercept here the network communication, yes? By seeing that you have 2 encrypt requests instead of 1, you could identify that something's happening. Or by logging this receiver CKMD to see that you have a mass of encrypt requests instead of decrypt. So you should have a symmetry ordinary by default. But so we have several countermeasures. They are mentioned in the in the paper, but thank you. Yes, obviously this is there are some mechanisms, but by default, so today's system are rather bad at this.
Very cool. Thank you.
Thank you.
Scott?
Okay, yes. If I understand it, you are assuming the sender and receiver crypto engines are both compromised. If you assume that, can't they replace the GCM algorithms with anything they find convenient and use that as an exploit? Why is this specific to GCM?
They could, in theory, replace anything. So it was a the topic was derived from a rather applied project where we have an existing system, and there we have AES GCM, and yes, in theory you could replace also some messages. You could introduce some additional information, but we try to stay with the minimum of exploit that is needed to transfer information, and in this case just the authentication tag is sufficient, and you have obviously you have external observers too that could intercept some changes in communications.
All right, thank you. Can you please stop sharing slides?
Yes. Okay, thank you.
All right, thank you very much. Next is Dual Prf construction, Nimrod. Just a second.
Yeah. Can everyone hear me and see the slides?
Oh, okay, fine. Hold on. Did you? Okay.
Ah.
I'll just yeah. Okay.
All right. Can everyone hear me and see the slides?
Yes.
Yeah. All right. So hi, my name is Nimrod Aviram, and I would like to present a Dual Prf construction. This is joint work with Benjamin Dowling, Ilan Komargodsky, Kenny Patterson, Eyal Ronen, and Eilon Yogev. So in modern protocols, we usually have the client and server agree on a shared cryptographic secret along with other protocol parameters. And then we feed that shared secret and the protocol transcript into a KDF, a key derivation function, to arrive at a per session shared secret. And from that shared secret, we derive symmetric keys. That key derivation function should be pseudo-random. That is, the output should be indistinguishable from random when the key is uniformly distributed, even for an attacker that fully controls the transcript. So we can use HMAC, which is provably a PRF under very mild assumptions. And it would appear everything is well and good. However, in some cases, we have more than one key. And now we're asking, what should we do here? For example, in TLS 1.3, where we use both Diffie-Hellman key exchange and the pre-shared key, and this happens a lot, for example, in resumption, which is very widely used. In hybrid key exchange, where we have both a classical key exchange algorithm and a post-quantum one. And in the signal double ratchet protocol, where we combine an existing shared secret state with new keying material that is output of Diffie-Hellman. In all of these situations, we use two keys, at least two keys. And the general approach for doing this is to combine the two keys into a single unified key using a key combiner function, and then compute HMAC with that key over, say, the protocol transcript, and have that be the output of the entire KDF. This is largely done both in existing constructions and in our proposal. And when we say that key combiner function takes two keys, we mean it should be a dual Prf. That is, the output should be indistinguishable from random when one key is uniformly distributed and the other key might be controlled by the attacker. And this scenario is actually realistic because, say, in protocols, an attacker can replay a key share from a previous session and attempt to learn that key, while injecting new keying material from to the other key. And of course, we don't know which key the attacker controls and which key the attacker attempts to learn. So it's then natural to ask, can we use HMAC as that key combiner function? And the answer seems to be no, because HMAC is generally not a dual Prf. To be fair, it was never claimed or designed to be a dual Prf under any assumption. And it's definitely not one if the underlying hash function is not collision resistant. And that's where our proposed construction comes in. So we have a construction for a dual Prf. The construction uses an underlying hash function as a basic building block. That hash function can be, say, SHA-256 or any other standard hash function. It doesn't even have to be collision resistant for the construction to be secure. The whole construction is fully practical. It only uses symmetric cryptography and is overall cheap to compute, and we'll get to that in a minute. It's especially cheap when we compare it to asymmetric cryptography. So if we want to use it in protocols, which we mostly do, the relative cost for including the construction is minimal. And we have a security proof in our paper on ePrint. How do we compute our construction? We take the first key, prepend some common reference string to it, run that through the hash function, and use the output as the key for HMAC. Then we take the second key, run it to through a new function, which I will describe in the next slide, and expanding injective one-way function. We take the output, prepend some common reference string to it, and use that as the data input for HMAC. Then we do the same thing again with the key rows swapped. We then take the two HMAC outputs, XOR them, run that through the hash function one last time, and this is the output of the whole construction. Note how everything here is symmetric and standardized cryptography, except for the F function, which I will now describe. How do we compute the expanding injective one-way function F? We have a message M, and we split it into blocks with the same size as the hash function block size. Then for each message block, we run it through the hash function several times, each time while first processing an input block of an appropriate index. So we first prepend a full input block of zeros, and then the message, and we run that through the hash function, and we get the start of the output. Then we do the same thing again, but with the whole block of ones at the start, run that through the hash function, and get the second, we get the continuation of the output. We concatenate the hash function results of all of these computations, and this is the expanding function f. Note that it is also symmetric and cheap to compute. In this diagram, we process each block twice, but this is only for simplicity. In practice, we propose processing each block 3 times. The amount of times we process each block is called the expansion factor, and this is a parameter of the construction. And why do we choose an expansion factor of 3? So what this expansion factor does is it helps the function be injective. The more we expand the input, the longer the output, and the higher the chance that the function is injective. If we want to standardize and deploy a new KDF, this has high potential for ossification. That is, once we deploy something into the field, it will be very hard to upgrade. And we're still dealing with these situations now. So we want to be conservative here. So we assumed that whatever hash function we use will eventually be as broken as MD5 is broken today. So even with MD5 and current cryptanalysis, taking an expansion factor of 2 is unbreakable to our knowledge. And taking an expansion factor of 3 seems like a good security margin. We are also open to taking other values for the expansion factor. We said the construction is fast. It's much cheaper than asymmetric cryptography again. It takes roughly 7 microseconds to combine 2 keys. Comparing that with, say, HKDF using concatenation, HKDF takes roughly 1 microsecond, so the overhead is roughly 6 microseconds. And this is very cheap compared to asymmetric cryptography. So even just doing Diffie-Hellman over X25519 with 2 exponentiations per connection, each exponentiation takes roughly 45 microseconds. So just Diffie-Hellman is about 19 microseconds. Doing ECDSA takes either 80 or 25 microseconds. And if we want to also use entry, that would add some more. So the largest overhead we came across is when doing only 2 Diffie-Hellman exponentiations and a signature. And even then, the overhead is only 5%. This is the largest overhead we know of, and the overhead is lower for probably most other use cases. If some people find the overhead unacceptable, we can consider an expansion factor of 2, which would make the construction speedier. What do people use in practice instead of dual PRFs? So we've spoken of TLS 1.3 in Diffie-Hellman plus pre-shared key mode, and of Signal, which combine keys using HKDF, which is equivalent to HMAC. This would imply we think of HMAC as a dual PRF, even though it is generally not one. In hybrid key exchange, where we combine classical and post-quantum key exchanges, both in the IETF work and in similar proposals from Etsy and NIST, we actually concatenate 2 keys and then feed them to the KDF as usual. And even with only a single key, in TLS 1.3, where we only use Diffie-Hellman, that Diffie-Hellman output is actually passed through the message input of HMAC, which would again imply we treat HMAC as a dual PRF. So we think standardizing a dual PRF would help make protocols more robust, both with multiple keys and also with a single key. And we're asking, we would like to write an internet draft, and we're asking, are people interested? Thank you. I'm happy to take questions. Yeah, Chris Wood, please go ahead.
Yeah, thanks. I have one question and then more of a comment. The first of which is on the claim that HMAC or HKDF extract is not a dual PRF. Not a cryptographer, so I defer to you experts to determine whether or not that is or is not true. But my concern is that many of the proofs that I've seen for TLS 1.3 do assume that HKDF extract is indeed a dual PRF. So I'm wondering if you can comment on what the impact of this particular claim is on existing security analyses for protocols like TLS 1.3, and in particular the key schedule of TLS 1.3. A second comment is on the idea as to whether or not to write a draft. I think having something that has like rigorously proven dual PRF properties would be nice. However, for applications like MLS, which require more than one key as input, it might be nice if an NPRF was the construction output on the other end. I know Chris, forgetting his last name, proposed for MLS specifically an NPRF construction. I don't know, or I don't recall what came of that, whether or not it turned into an internet draft or there was a paper published or not. But I would like to see it perhaps generalized beyond just two inputs. Really curious to hear about the first question.
Thanks. So I will start with the second comment, actually. We can accommodate however many keys is needed, and we can do so efficiently. So we think we can help there as well. And as for existing analysis of TLS 1.3, I guess it's complicated. A lot of analysis doesn't reduce to any specific assumption on the hash function or on HMAC, but rather to something which is kind of a toy protocol, like the PRF ODH assumption.
Well, I just I pulled up a paper from who is it? Sorry, scrolling up.
Actually,
Ben Delling, Mark
if it's okay.
Doug.
I'm sorry?
Sorry?
Yeah, I think we're just running out of time. So I would say that we have an extensive discussion of this on our paper on ePrint, and we can take it to the list if that's okay.
Sure. I just wanted to just comment briefly that like they in various proofs they do use this assumption to bound to make certain bounds on like adversarial advantage, and their hops amongst various games. So it does seem relevant, and I'll take a look at the paper and we can try offline.
Yeah, and let's discuss this on a list. I'd be happy to.
Okay, quickly, Christopher.
My question is why? I was curious about like your benchmarks. This seems comparable. Like, is this comparable to what HKDF does? Why compare it to? What's the value of comparing it to like asymmetric crypto?
So we're trying to argue that if we add this to a protocol, the overhead is minimal.
Okay. Because So I think I guess the comparison, the one apples to apples comparison is HKDF, right? So like if it's comparably fast to HKDF, we're in good shape.
Yeah. So it's slower than HKDF, but we think it shouldn't matter that much because we only do it once, say to process a different.
Yeah, I totally agree. Yeah. I don't think it's the overhead's insane, but I'm just saying that's the benchmark, right?
Yeah.
Okay. Just want to be clear. Thank you. Very, very, very cool construction, by the way.
Oh, thank you. Do we have time to hear from Philip?
Yes, I closed the queue after Philip. So Philip, quickly.
Yeah, I like this a lot. There are some other things. If we're going to revisit HKDF, there were a few landmines that I came across when I was trying to use it in the mesh. Some of the assumptions that are reasonable to have as a user about what certain inputs will do are not actually true, and that just hit me a few times in way there was surprise that should be eliminated. The other point I make is you're looking at HMAC. I think that that's the right thing to use as far as timing is concerned. But if I was going to move to a different key derivation function at this point, I would not want to use HMAC. I'd want to use KMAC, because HMAC is a hack trying to make a digest function that wasn't designed to be a MAC do that. KMAC is a construction that is designed to be a MAC in itself, and I think it's a lot more principled. So I think if we go to standards on this, we should definitely have KMAC in there as a recommended algorithm, and I would like to see it the favored algorithm.
All right, thanks. I'm not familiar enough with KMAC to comment on this, and also other than HKDF.
Yeah, it's just using SHA-3 in a principled way to do a MAC, because it's,
All right, so a MAC is not always a dual PRF, but I think we should discuss it further on the list if you would like. I'd be happy to.
Okay.
All right, I guess that's it for me. Thanks.
All right, thank you. If you can stop sharing slides, that would be great.
How exactly? Oh,
actually, that might help.
there we go.
All right, fine. Okay, the next one is the Aegis family of authenticated encryption algorithms. Okay, let's do that. Okay. Shall I pass controls to you, or do you want me to drive? I can do it either way.
I can do it myself. It's okay if you pass control.
Okay. Okay.
Okay, so I'll introduce the Aegis fast authenticated encryption family. There was an internet draft with first version written last September. There is further support from Google, and also in the team are the two designers of Aegis, Hong Jung-woo and myself from University of Leuven. So it's a family of authenticated encryption algorithms. It's nonce-based. It's twice faster than AES GCM. So on the benchmarks, we get to 0.287 cycles per byte. Family offers a high security level, and there is already multiple implementations available, including one in the Linux kernel. A few things about the design. I'll be very brief and not go too much in boring details. The design was actually inspired by Pelican Mac, which is a Mac designed by the AES designers to be faster than AES, because for a Mac you can be faster. And we then turned this into a stream cipher, which is actually also a lot faster than the AES. So we have a 128-bit key and IV, and all the words are here 128-bit. But there is a large state of 8 times 128 bits, so 1024 bits in Aegis 128L. The scheme is very modular and easy to analyze. So you take your key and your IV, you do 10 steps of the Aegis operation. And then for every next step, you accept 2 message words, you produce 2 key stream words, which you add to the plain text, and you output the ciphertext. Then at the end, you add some linked information, and then you do 7 more steps, and you get a 128-bit MAC value out. So it's a stream cipher with built-in MAC generation. So inside the Aegis operation, so there is 8 blocks, and they're updated. They all use 1 round of AES, and they're updated, as you can see, in parallel. You see also the injection of 2 message words, and then to compute the output, we take for each of the outputs 4 message words, and then 2 are added and 2 are AND, and then added to the rest. So this is more or less how it works. So I think it can be described in a very simple and compact way. Security properties, we propose 2 variants. The 128L variant has 128-bit security against confidentiality attacks and data authentication. There is also a 256-bit version that actually have has 256-bit security against key search, and we decided to keep a 128-bit tag, so have the 128 against forgery. For the smaller version, we allow use of 2 to the 48 messages per key, which I want to point out is much larger than what you can get for the same security level with, for example, GCM or OCB. For the large version with sticks, there is no restrictions on number of messages in practice. But we want to point out that if you would do 2 to the 128 attempts, you could do an online forgery attack. So you need a huge number of interactions with the verifier, and then you could shorten key search, but we decided this was not really a problem for security. Security properties are that unlike GCM, it's key committing, and this actually stops certain key partitioning attacks. I don't have time to go into detail. GCM also has some issues when you vary nonces. You may get some security problems. So this is not a problem. We recommend here to have maximum size nonces, but they can be shortened. What we don't achieve is resistance to nonce reuse. We don't also achieve resistance to, or you could be in trouble if you start releasing plain text before you check the MAC. And we also didn't design a scheme that's compactly committing, could be used, for example, for franking. So these last 3 properties are by design. We believe that if you want these properties, you have to do at least 1 full block cipher encryption per 128-bit, and you can never be faster than AES itself. And also the same thing, the franking would require a larger tag, which we also didn't think was necessary. So there has been quite some independent security evaluation. The EG cipher was designed 9 years ago and was submitted to the Open CSAR competition. There were close to 60 schemes. And in the end, a handful of those were kept for the final portfolio, including Aegis 128. There has been some independent analysis by other teams. There has been some correlation analysis on Aegis 256. We are not concerned about these attacks. Of course, theoretically, it's below 2 to the 256, but they require between 2 to the 150 and 2 to the 160 ciphertext blocks. We're not concerned. And I spoke to the people who did this attack. They don't see how to improve it. They have done some attempts in the last year, but they didn't get much further than a small factor of 204. All very recently, this month actually, and this week at FSC, 2 attacks have been published on Aegis 128. It's actually not the version in the draft, but because in the draft we have 128L and 256. And they break about 5 of the 10 rounds with a reasonable complexity. This is interesting because it shows independent analysis. So this is an attack in which you vary the IV with chosen IV attacks. But we also want to point out that if you take 4 or 5 rounds out of 10 of AES, there is also quite efficient attacks. So we think this is normal that on an AES-based scheme, if you have only 4 or 5 rounds, that there is an efficient attack. And this is not a reason at all for concern. It will be very hard to scale up those attacks as for AES. And finally, performance. The scheme is highly parallelizable online for encryption and can make optimal use of the AES instructions. I'll just show you some benchmark numbers on the next slide. So Intel Skylake, as you see on the bottom, the speed goes up a lot. This is cycles per byte, so the smaller, the faster. Once you go above 1K messages, I zoomed in on the top, and there you see that it's about twice as fast as the GCM, and it goes down to the number I promised you, 0.2 something, 25 cycles per byte. We have similar results for ARM, which I will skip, and I conclude here now. So saying that Aegis is a very simple design, that there is a variant for 128-bit and 256-bit security. It's also easy to analyze, easy to implement, and it offers a very high security level. The design is targeted for platforms with AES support, but could also be implemented efficiently if there is no such support. And so there has been quite some scrutiny, and so far, all the attacks give us confidence is really a highly secure cipher. Thank you very much.
All right. Any quick questions, comments? Okay, Christopher?
No question really. I just wanted to say I think Aegis is a beautiful construction, and I would love to see it standardized. So I absolutely would support the work CFRG working on a draft.
Thank you.
Okay, Armando.
Hello. So I just want to know, how does it compare with other lightweight ciphers?
Well, EGIS is not exactly lightweight, it's a high-speed design. There is a NIST lightweight competition going on, and we didn't submit it there because we didn't think it fitted there. It's really more like a high-performance design. And NIST has announced that they will conclude the competition soon, but there is no results there. So I think in general, it's definitely one of the faster designs. There have been some more recent papers trying to do further optimizations, but I think those would definitely need another 5 to 8 years of cryptanalysis before they can be adopted. But there is extensive benchmarking available. I only showed you some brief details, but it's also faster than OCB, and it's faster than any other cipher that has this kind of scrutiny.
Okay, thank you.
Thanks for the presentation, and perhaps I missed it, but I'm wondering if you can comment on the sort of nonce reuse properties of this particular variant.
So EGIS is vulnerable against nonce release by design. It's better than GCM. In GCM, with one nonce, you lose your authentication key and you have a big problem. In EGIS, it's clear that there is a paper that was actually in our design document. The details were not worked out, but the paper has shown is it need to have 15 nonce reuses of one nonce, and then you can recover the state. Now, this is a design decision. We believe that if you want to be resistant against this, you need 2 passes or you need lower performance. We don't think you can achieve this performance for a nonce-reuse scheme. So we warn inventors, implementers for this. This is also clearly pointed out in the draft that you have to be careful, just as for GCM, that you don't reuse your nonce. And luckily, the consequences are not as bad as for GCM.
Okay, thank you.
But do you have any requests for CFRG? Is it for our information for now, or do you want this to be adopted?
I guess this is. I guess we wanted to introduce it at least because I'm not sure it had been discussed before, and I think we seem to get some good feedback. We would like to get feedback, and of course, if there is consideration for adoption, we definitely would support that.
All right. Okay. Thank you. Okay. All right, thank you very much. Let's move on to the... Oh. Okay. Dan? Okay, hold on. I would just drive, right?
Yeah, please.
Mm-hmm.
Okay, thank you.
We just, oh, okay.
There we go. Rock and roll. I'm Dan Harkins, so this is a proposal for making some changes to HPK or additions to HPKE. So next slide, please. It was recently published as RFC 9180, and so I think it's a good time to make this ask again. The issue is that HPKE is a really nice construct, and I like it a lot, but it doesn't work for some use cases. For instance, for devices that are operating in a constrained environment, the serialization and deserialization for the NIST keys is over twice as long as it needs to be. And so I'm proposing that we could address that by using the RFC 6090 compact output serialization. Another issue that I have with HPKE is that it doesn't work on lossy networks. It assumes that there's guaranteed in-order delivery of all the packets that are being used. And that's because the sequence counter that's being used with the AEAD cipher is completely inside of the context, and the user has no ability to know what the sequence number is or to have any control over it. So if there's any packet loss or packet reordering, the sender and receiver get out of sync and everything just falls apart. And since the internet does not provide guaranteed in-order delivery of packets, I think that this is a problem we should address. So for the first one, it's pretty easy we can solve that by just assigning some new chems that do a compact serialization. But for the second problem, next slide, please, I have a couple of proposals. One of them is we can use a deterministic AEAD and not worry about the nonce. If the nonce is causing problems, then let's just use something that doesn't care about a nonce, like SIV. Now, of course, SIV has problems regarding some of the security of the deterministic mode, but you can achieve semantic security with SIV if the plaintext carries enough probabilism that the nonce normally would have provided in a normal EAD scheme. So for certain situations where you can have that guarantee, I think a deterministic EAD mode with HPKE would be acceptable. If not, what we could do is use a rolling replay window analogous to what was done with IPsec in RFC 2401, where you've got a bitmap of received packets, and that allows you to receive them out of order, and some can get dropped. Packets that are way too old will get thrown on the floor, and the window advances as you verify received packets. Of course, this requires access to the sequence number. The receiver has to know what the sequence number is to determine whether it's valid in the receive window or not. So that would require us to export the 4-octet sequence number into the ciphertext. This shouldn't be a problem because that information would already be known to any sort of attacker who can count. And we're not going to be exporting the secret nonce. We're just going to be exporting the 4-octet sequence number that gets XORed onto that thing. So next slide, please. So what I'm asking for is 3 things. I want to add new chems for the NIST curves that do compact serialization. I'd like to add support for AES-SIV as a deterministic cipher mode in HPKE. And for the situations where AES-SIV would not be appropriate on lossy networks, I'd like to have a defined way to use RFC 2401 style replay window to deal with packet loss and reordering. Next slide, please. I do have a draft. It's in the 01 version. Please take a look. And I also have running code. If you want to take a look at my GitHub, there's a HPKE wrap. It's fully compliant with RFC 2401. It handles all of their test vectors. But I also added additional test vectors to do compact representation with new chems and deterministic authenticated encryption with SIV. I just basically stole a couple of values from the reserved number space, but hopefully that won't be a problem. So please take a look. Next slide, please. So we have running code, and I hope we can get rough consensus to adopt this as a work item.
Okay, Stephen.
Hi, Stephen Farrell. A couple of comments. One is there's with 9180, when I combine all the chems and KDFs and so on, I have 480 different combinations of algorithm. So there's already a lot. However, these seem like reasonable changes. The other comment I have is maybe HPKE should be thought of as moving from CFRG to an IETF context, because perhaps the part where we needed CFRG expertise is in the past, and these kind of changes seem like more engineering changes than CFRG-like changes. I wouldn't be too focused on it, but just for things like changing the point representations, that's like a that shouldn't require
So you're saying dispatch me to sec dispatch, basically.
No, I'm not recommending that. It just occurs to me that might start to make sense, because maybe the cryptographic bits of this are mostly done, and it's more about kind of engineering at this stage.
Fair comment.
And then actually I have one question. So does your code now include the kind of X25509?
No.
Okay, so it's just the NIST curves for now still.
Yeah.
Okay, cool. Well, otherwise I'd be supportive of this happening. I'd probably be a little bit happier if it didn't happen immediately. I don't know. I'll have to think about it. So doing this sometime, yes. Maybe here, maybe elsewhere. And,
okay.
Yeah.
All right. Thank you.
Okay, Chris.
Yeah, thanks, Dan. I also think that these are perfectly fine additions. Well, the chem with the different compressed format is a fine addition. I'm a little bit concerned about the deterministic AED and the implications it has on how you use it. So I prefer. I'm less, I guess, less supportive of that. But I guess as a meta comment, this is or question. This is not directly to you, but more for the chairs. I'm realizing now that we don't really have established any designated reviewers or experts to review these IANA registry additions. The registry policy for editing anything, any new chem, AAD, or KDF is specification required, which doesn't require this to be published or adopted or anything. It just requires a document to exist and then approval from one of the experts. So do we need to establish experts to review these requests so that we can get Dan's algorithms in the registry?
So yeah, typically what happens is IANA asks for experts on first request. So I suppose that's kind of constitute a first request. So yeah. Can you email chair as a reminder to just double check and investigate this specific question?
Okay.
Sure. I mean, in TLS, for example.
As well, yeah. Well.
Yeah, but this would be the specification that would be required, right? I mean, if it's specification required, there has to be some published document, yes?
Yes, but it doesn't have to be, it can be like independent stream or IETF stream, or doesn't even have to be an RFC.
Okay.
I think.
It can be a draft.
Right, Rich, I don't know.
Which is slightly more controversial, but you know, some people tend to think that's okay. Well, if there is enough support to do this, it seems like it's a relatively simple and smallish document. So yeah, we should just, we already done like, you know, extra LMS extensions, for example. I think without consulting with my co-chairs, I think the bar for reasonable extensions is a bit lower.
Okay.
So if there is enough interest, let's do that. Christopher?
Yeah, I just wanted to say that was specifically why we want a specification required for the policy, so that you don't have to go through the whole process of publishing an RFC just to get something in the registry, to make it easy to add new things. So less work overall for everyone. But I will email the chairs and see if we can get the designating experts set up.
Okay.
Thank you.
Okay.
Is that it?
I think that's.
We had another Christopher in there, didn't we?
He just took himself off.
All right. Great.
We have 3 minutes left, and Chris sacrificed one of his presentations. We basically used up all of this time, so I don't think there is a point. Unless you want to say a few words very quickly.
Yeah, thanks. Yeah, there's definitely not time. Just wanted to give just a brief summary of what I was going to talk about. It was mostly going to be a reflection on the documents that the CFRG is producing right now and has produced in the past, and their sort of importance in the community, in particular the IETF community, and how they use CFRG specifications for specifying protocols, conducting security analysis and whatnot. Trying to point out that there are there's probably a number of ways in which we can improve as a group the output of the documents in terms of clarity, consistency, and correctness. And it's kind of a plea for people to for volunteers who are interested in like sort of the editorial production of these documents to brainstorm things that can be done to improve document quality, be it with respect to the pseudocode that's produced, the terminology that's used in the documents, you name it. And I won't go on the slides or anything, but I'll try to summarize and send a message to the list, because I think there's something we can be done that can be done here. And that's it. Thanks,
okay,
Maxi.
thank you very much. All right, and with this, we have 1 minute left, which I give back to you. Thank you for coming. And see you online, and hopefully again next time. at least hybrid meeting, maybe even fully fledged one.
Thank you. Goodbye.